All right, I got the recording going now. Here we're starting week 2 for algebra. We just took a couple minutes to look at some PEMDAS related problems, especially involving parentheses that tends to trip people up. And since we didn't get to talk much or as much as I would have liked about multi-step equations last week, that's where I want to start off. And we will be talking about proportions today also, maybe even literal equations, if hopefully we get to that point. So we're going to just look at the odd number problems to begin with. I got to clean the board here. So you guys at home, take a look at these multi-step equations. Now we're really talking algebra. Got lots of variables. Got like terms we got to get together. And we got some decisions to make. Just take notes. I know you don't. If everybody were in class together and we were doing our normal 4 classes a week, 3 hours a day, we would spend 45 minutes probably just on this handout. We don't have that kind of time, unfortunately. So hopefully everybody at home can see these also. So the first problem, I got more than one x term. Well, that should be a clue that you need to combine like terms. And that first one was really only a 2-step equation. So how many x's do we have in that first one?
2.
I have 2 terms. I got negative 10 x's. Remember, combine the coefficients. Negative 4 and negative 6. So that negative 4x in the first column, that's 4 negative x's. It's not just 2 x's. Okay, we need something to write with or take notes on. You should get some paper over there. And then I got 6 more negative ones. It's 2 terms that have x in them, and they both happen to be negative. So we go to the integer rules because we're combining the coefficients, right? Same sign, add, keep the sign. The first rule that we went over last week for integers, same sign, add, keep the sign. So if both of those had been positive, we would have gotten a positive 10x. Now there's only one more thing to do. We're trying to get x by itself. Remember, the main goal in all of these equations, we want to isolate the variable. The variable's got to be isolated. It's got to be by itself. The coefficient has to be 1. We've got to get it to where there's just a single x there, and preferably a positive x. I got another person. Yep, you got a chance. And Renata's here. Okay, good. And you'll hear me say, what kind of a problem is this? I don't know. It looks like just negative 10x. Well, there's an operation in there.
It's negative 10 multiplied by x.
It's negative 10 times x, that's right. Because remember now, we're not going to use x to show multiplication anymore because it's the most popular variable. We can write multiplication in a bunch of different ways now. If we have an integer and a letter right together, with nothing in between, it's always multiplication. So then we're going to undo the operation, undo whatever the operations are to get to isolate the variable. So since that's multiplication, I got to divide. And I want to keep the equations balanced. You think about a balance beam or a teeter-totter, you put a weight on one side, you want it to balance out. When I divide here by negative 10 on both sides, that's kind of the weight that goes on the scale. So if I put it on one side, I have to put it on the other side also to keep it balanced. Equation solving is always going to be like that. You can't do something to one side and forget about doing it on the other, or we're going to get an answer that's all wrong. And when I divide negative 10 by negative 10, I get 1. Over here, it's not just 1, it's 1x. Over here, I got negative 20 divided by negative 10, it's 2. I don't need to write the 1x. If it's just a single letter, it's understood that it's just 1. The coefficient is 1. Questions? Anybody? I'm continuing to try to check the chat here, so if you guys, yeah, good, Kristen. If you guys got feedback here or got a question, try to post it in the chat and I'll come back. And the problem that I've had is when I post or when I show my screen with a handout like this, I can't do it on my phone also. Got a couple on it? What? Yeah, we're going to do that today. Yeah, those are called literal equations. That's exactly the same, though. Same process. Isolate the variable. Undo operations. It means we use the opposite. And keep everything in balance. Okay, so if we look at number 3, here we got 8x minus 2 equals negative 9 plus 7x. And we have an x term on both sides. And this is where we said we got to make decisions. This is a good example. Thursday, I think I mentioned how much I dislike negative variables because it's an easy way to mess up. If I forget it's a minus sign. So the first decision I try to make is getting the variables on a side where they will be positive. So here, this is just a matter of getting everything on one side or the other. But again, I'm going to use my opposite. Here, I got a positive 8x. I got a positive 7x. So the opposites are going to be negatives. Well, 7 is less than 8. So I'm going to subtract 7x from both sides. Because that will allow the 7x on the right to cancel out to 0x. 0x, 0 times x, it's still 0. We don't need to show it anymore. It's gone off the right-hand side. On the left, it's 8 minus 7. That leaves me with 1x. So once I made that decision to go to the left with my x's, now I got to send the integer to the other side so that my variable is isolated. That's a -2 or -2. X equals -7. And you can always check your answers on any of these. Plug it back in where x is. Do the calculations. Since these are equations, one side has to end up being equal to the other. Everybody okay so far? All right, now number 5 is one of my favorite problems. Anybody want to guess why? Say that again?
It's gonna be 0.
What's going to be 0?
And
M's going to be 0. What do you mean? We don't have any M's left?
1.
Do we?
No.
Ah. Right. So in number, and this is why it's one of my favorites, because this number 5 is actually a no solution problem. You'll see this a lot in, we go into higher levels of equation solving and graphing, especially no solution. Because when I solve this thing, I pushed it, it doesn't matter which way I push the M terms, they're both positive. So if I subtract 4M from both sides, I get -4 equals 0M. I lost all my variables. All the variables are gone. So is that a true statement? No, it's not true, which means there's no possible solution. It won't matter what number you put in there for M, there's no way those two sides of that equation are ever going to be equal.
I thought you like most solutions.
Because 0 times M is still 0. So if I took the M off of there, it maybe is even more obvious. -4 does not equal 0. And you'll see that a lot. True answers are solutions. Not true, no solution. There's another one further down the page that's like that also. We're not gonna end up doing all those on there today.
So when you solve the problem, do you have to put true or not true?
No, that's just an internal thought process that I go through. Does this answer mathematically it's correct? But as far as its real meaning, it's not a solution because it's not true. -4 does not equal 0. So at that point, once I've evaluated my answer and realized this isn't true, then the next step is for me to say, okay, that means it's a no solution problem. And you could leave it like this, but what I'm hoping that you'll do is to actually write no solution. Later on, when we start looking at graphing, we do systems. We have 2 parallel lines. Both of these lines have equations. They never cross. They have nothing in common. That's a no solution problem in graphing. You can have them in all different kinds of situations.
So if they're perpendicular, it's no solution.
Parallel. Perpendicular, that means they're crossing at a 90-degree angle.
So that would be true. So
Perpendicular means you got a solution.
So as long as they cross at some point, there's a solution.
Yeah, that's the shared solution, yeah. I'm getting into next week's, actually 3 weeks ahead of stuff with that, but it's just another example of a no solution problem. If you're curious about the other no solution problem on this handout, I believe it's number 19. But let's look at number 15. With variable problems like this, like 15 and others, we can't really do PEMDAS because of this variable. But we can still get rid of the parentheses by doing the distributive property. And that's part of this being a multi-step equation. Distribute that 2 times each term that's on the inside. 2 times 4x is 8x. 2 times -3 is -6. Bring everything else down. The process isn't going to change. You're just going to end up doing the same thing over and over again. We simplified this. That's really the first step. Now, what do you think the next step should be?
Bringing
Distribute.
one of the x's and combine.
You could do that. I like what Amanda says. She wants to combine like terms first. And on this side, I see a -6 and a -8. You could still do what you said. So let's do that first. Because there's nobody that's going to tell you that that's the correct order at this point. If that's how you see it being solved, then that's what you should do. So now I got 6x. Now I can combine these like terms. So whether you do it at this level, the next row, or the next one, doesn't matter. Do those two combine to that, -14. I can add 14 to both sides. Then I'm using a positive for a negative. If all I'm doing is canceling, positive for negative. And then I got 6x equals 18. Divided by 6, that's the opposite at that point, right? 6x equals 18. Now it's just one final step. X is 3. So if I went back to this original and plugged a 3 in here, any place I saw x, if I did it on this side, did the calculation, it should equal the other side once I did the same calculation. And that's the true nature of equations. You have an expression here on the left side that's equal to the expression on the right side. No matter how many terms they throw in there. So what I'd like you guys to do is try number 17. So you guys at home, take a minute and try number 17. I'm going to pause the recording. Okay, well, looks like another technology problem day. I forgot to turn the recording back on, so I missed a lot of that. Print from home. I'd have to email it to you, Chance, but the problem with that is the second page has the answers. So I'd have to manipulate it so you just got the problems, which I can do. Questions, anybody? All right. So we did some problems there with multi-step equations. Now we're gonna go to a special kind of a multi-step equation. And here we have what are called proportions. Let me pull the screen down for this one. Okay, has anybody ever built models? Model cars, model planes, you know, model rockets, any of that kind of stuff. Proportions is all about scale. Think about what architects and engineers have to do. Architects and engineers have to deal with proportions all the time. Because if an architect is designing a building, they can't design it on paper to the actual size that the building is, right? Nobody could ever do that. So architectural and engineering plans always come with a scale. Engineering plans, especially if you do it, as I used to build subdivisions. You're looking at water and sewer and street plans. Typically the proportion is 1 inch equals 100 feet. So that could be written as 1 to 100. 1 inch to 100 feet. That's a simple proportion used in engineering all the time. If you look at the examples here, they all look like fractions. That one I just wrote looks like a fraction. The first example here is 3/4, 3/4. The second example writes it with a colon, a double dot, 3 to 4, 3 is to 4. The third example just writes it in words. Those all refer to the same thing. It's the same proportion, 3 to 4. So if I'm going to draw plans for this bookshelf, or I need to make a scale model, and I want it to be at 3/4 scale, is that going to be bigger or smaller? It's going to be smaller. I'm downsizing it. Because for every 3 on one, the other is changing by 4. That's really what proportion is. Same thing here on my engineering plans. So for every inch I move on the plan, it actually represents 100 feet. So we're not going to worry about drawing plans or any of that sort of stuff. But understanding how to solve proportions is what we got to do. And it's not that complicated. It's just another form of multi-step equation. Yes, exactly. Yep.
I should not have used some of this.
Have you worked in construction?
Yeah.
Oh, great. Yeah, house plans a lot of times are 1 inch equals 20 feet. Because obviously, you don't have as much, you're not dealing with a whole bunch of land, you're just dealing with individual houses.
Sometimes it's completely poured out, or they have it like an inch too short, and messes up the entire house.
Yep. All that kind of stuff's possible. People misread the plans, and they don't do the calculations correctly. Concrete's especially tricky because concrete's usually delivered in cubic yards. And so if everything you measure is in feet and you don't do the conversion correctly, you're gonna end up with way too much concrete. What you see here are two proportions. 1/2 equals x over 6. Now, these words, extremes and means, don't worry about these. 1/2 equals x over 6. The key thing for proportions to remember is they function like equivalent fractions. So I got an x here in my second fraction. There's a couple of different ways I can figure out what x is. What do I have to multiply 2 by to get 6? That means if I multiply this by 3, I gotta also multiply the top number by 3. The same kind of balance idea. I can't manipulate one term without changing another term exactly the same way. Well, that will give me 3 over 6. That's a simple example. What we want to be able to do is to learn how to do something called cross multiplying. That's all this extremes and means crap means on here. It's multiply the extremes times the means and they make them equal to each other. Well, just cross multiply, make the products equal to each other. Because when I do that, I got 2 times x equals 1 times 6. Now it's a one-step equation. Solve for x, just like we were doing before. Divide by that coefficient. X is 3. Where that's important is where you get into some more complex proportion. That's a simple proportion that you could easily see as fractions that are equivalent. Focus question 1 is very similar. But if we get to this next question, focus question number 2, not quite so easy. The process is still the same. Still not cross multiply, make the products equal to each other. I usually start with the upper left and go to the right. That's the one I'll put on the left. So this would be the first one, 2 times x plus 9. And if you notice, I put that x plus 9 in parentheses because what it does, it's a quantity. Whatever x is, it's plus 9. So I got to work with those two together as a quantity, and it sets up a distributive property problem. The other cross is easier. 6 times 8 is 48. So here's how you can see where it starts to get into a multi-step equation area. Distributive property, 2 times each term inside, 2x plus 18 equals 48. I got one x term. So I'm going to get the integers together on the right, canceling the 18 with a negative 18. Remember, this is a, I'm using these 0 pairs to get rid of stuff. It looks like I'm getting rid of it, but I'm actually using it on the other side. So 2x is 30. Final step, almost always the final step is divide by that number that modifies x, that coefficient number. So I get x equals 15. I don't know if that's a good answer or not. So we'll go back to the original problem. X plus 9. Okay, all I did was take the 15 that I got for x and I replaced the x in the original problem. I can set the order. I can cross multiply anymore. got all numbers. I don't have a variable. That's the main reason we got to cross multiply, is to be able to deal with the variable. Well, 2/6 better equal 8/24. Are those equivalent fractions? Yes, they are. 2 times 4 is 8. 6 times 4 is 24. Anytime I can multiply both the top and the bottom by the same, I'm going to get an equivalent fraction. I can multiply by 5, I can multiply both by 10. It doesn't matter what the number is. But to know if you got an equivalent fraction, that's how you check it. Are these both being multiplied by the same larger numbers? Yeah. Multiply by 4, multiply by 4. If this was 8/25, no, now it's not equivalent. I can't even multiply 6 by anything equally to get 25. I'm just saying that to demonstrate. Equivalent fractions. Equivalent fractions are just the same amount, just divided into different size pieces. Questions, anybody? All right, now looking at focus question 3. Twice as much fun. Maybe not. In fact, I'm sure probably not. And same process though, cross multiply. I got a quantity here. This quantity times that. 10 times n minus 1. Whoops. No, that's n. Here's a quantity times this. Equals 8 times n minus 5. Okay, now all it did was just add another distributive property problem. I got one on each side now. And then n minus 10. 8n minus 40. Okay. I always like to move my variables first. I'm going to move the lower number to the side where the higher number is. That's going to make sure that I keep, especially when the higher number is positive. I keep saying move, but I'm really canceling. You know, earlier, on the last problem, I used numbers. I used 18 and negative 18 as a zero pair. On this one, I got terms with a variable. That's a zero pair also. Because 8 minus 8 is still 0. 0n is still 0. Thus, the zero pair. 2n minus 10 equals negative 40. Now I got another zero pair here to create on the next line with just the integer negative 10. 2n equals negative 30. So what's n going to be? Negative 15. Very good. And that's all there is to proportions. Cross multiply and make the products equal to each other. Questions, anybody? All right. See everybody on Thursday. Thanks for being here.